Good afternoon, everybody. Good morning to those who are in a different time zone. Today, I'm going to be presenting you the ICT Tech Talk number 28. This time, it's not Praveen, it's me. It's my special honor to present to the speaker, Dr. Zachary Pardos. I've known about him for 10 years. I've known him personally for 9 years. Zach, can you advance the slide, please? Right, so this is what internet knows about Dr. Zachary Pardos. He's a learning analytics, educational data mining, machine learning researcher, received his PhD from Worcester Polytechnic Institute. He was a postdoc at MIT with Dr. Pritchard. He is now a professor at University of California, Berkeley, has a staggering number of citations to his literary works, over 2,000. Something you might know if you Google him is that he was the student team runner-up. He alone was a student team ATT 2010. So the first place were the guys that had 2 faculty members and 2 full classes of students. So he put up a really great fight there. Has over 100 published works, and he is active as a researcher since 2006, so for 15 years. He used to be an EDM, well, actively involved in EDM. Then he transitioned into the field of massive online open courses. Right now, he focuses on recommender systems heavily, still maintaining his research track with MOOCs and EDM. EDM is not electronic dance music; it's data mining. Right, frequently confused when the conference is active and there are people talking about it. So Zach is going to talk about a series of research projects he did at University of Berkeley, including and limited to the system called Ask OSCE. And with that, I give you Dr. Zachary Pardos. Zach, take it away.
Thank you, Michael. Real pleasure to be introduced by a longtime colleague and friend, Michael Udelson. All right, thank you for the invitation, everyone, and for attending this remote tech talk. So I'm just gonna get right into it. The title is Leveraging Content and Context for Course Recommendation in Higher Education. And I'm gonna start by saying what I mean by content and context. So throughout the talk, I'll be discussing several different paradigms of recommendation that have been brought to bear in our course context here at Berkeley, and then extended elsewhere. But in all of these contexts, I'll be leveraging, the models will be leveraging one or both of these sources of data. So here's a college course, data structures, CS61B. You see the catalog description, and then you see a sample of 2 students and the course history of those students that involve 61B. So this is what I'm referring to as the content, the semantics, literal semantics, natural language describing the course, and then there's the context, which is also akin to the kind of data that's usually in collaborative filtering. So what was the behaviors of users with respect to this item, and what can you say about the item given the behaviors? Okay. So why do we need recommender systems in higher education? Well, there's a couple reasons. One is the emergence of data science, which is attracting students from all different majors, all different backgrounds, and they're all asking questions like, what is an appropriate first class to take in data science? Do I have the appropriate background? What are the careers in data science? And so this is leading to a lot more demand on faculty and other experts, such as non-faculty academic advisors, to guide them. But not only is there not enough of these experts to go around, they all have their strengths and weaknesses. Faculty, for example, have local expertise, deep knowledge within their subject area, but if you start to ask them about the department next door, they're less, and the courses, they're less familiar. The academic advisors, tend to have broader familiarity across departments, but less depth. Then there's machine learning, which could theoretically benefit from breadth and depth learned from big data across the university, but of course, models lack the ability to easily tease apart the difference between correlation and causation based on just observational data, unlike humans. So they all have their pros and cons. There's also only a 40% four-year graduation rate in the US. And depending on if you're at the university or community college level, the advisor to advisee ratio is 1 to 400 if you're lucky, or 1 to 1,000. And then lastly, the future of work. This is a coffee making machine that is in our first floor of the Graduate School of Education building. And it's manipulating regular human coffee making machines. It's kind of a novelty. It's fun. It has a name. But we know this is going to be a more and more common sight, which means people are going to be looking to get re-educated, to shift careers, etc. And we're going to have to be ready with advice on how to get that re-education. Graduation planning is also hard. If you're, this is at a community college, and this is what it looked like for me, probably for many of you. If you want to know what you need to graduate, you consult this PDF that tells you the topics, the categories you need to satisfy, what courses satisfy them, and then you need to look up what course is available in the current semester that you haven't taken. And then by the time you get to that result, you kind of forgot what you're doing. But it often requires several tabs open in a web browser to figure out what you need to take. So that planning aspect can be improved, and that's just a simple information system issue. What is less of a simple information system issue are these more explorational questions, like where do you start as a student? How are courses conceptually related to one another? Are you ready to take a course in a completely different field? Intellectually, are you ready to take French Lit if you are a computer science major? Maybe you're curious in it, but you really want to know how hard is it going to be for me? And will a particular course count for credit at a school that you maybe want to transfer to if you're in a 2-year program? So these questions take some amount of inference and modeling to be able to answer in a satisfactory way. So on top of all that, as the motivation, there's also the challenge of applying technology while retaining institutional values. And why that is important is because if you're a recommender system and you're personalizing, that means you have a relationship with the university whereby they are granting you the privilege of data. And you as a recommendation provider are essentially providing a form of guidance, right? That is sort of not under the auspices of the institution. You're not an official academic advisor. And so, there is a incentive to understand what the institution values and to understand where your recommendations are going astray of that or where they are aligned. So let me tell you about the values that I've observed at the University of California, Berkeley. And the different stakeholders have different values. Students value maintaining GPA, getting a good job, maybe going to grad school, increasing socioeconomic status, which tends to also be the goal of the government. Faculty tend to want students to find their passion, deeply understand course material. Administration wants students to get a well-rounded education, a pluralistic education. That's what they see as the value proposition of a liberal arts education, and also a big part of the Berkeley brand is you come here, you take these breadth of courses, and you leave a well-rounded individual and not over-specialized, at least at the undergraduate level. And then finally, advisors want students to graduate on time and not overextend themselves. They don't want those freshmen taking upper division courses and then running into problems and then getting slowed down. So what are the recommendation models that have a chance of addressing any subset of this? This is a tech talk, so we're going to be talking about modeling. So for maintaining a GPA, deeply understanding course material in the sense of being prepared for that course to then understand the material, and then graduating on time and not overextending, we have a goal-based recommendation approach, which I'll get into. For increasing socioeconomic status, we have an approach called cross-institutional translation. And the idea here is that a major proposition for how citizens, at least in California, increase their socioeconomic status is through our public education system, going from a 2-year institution to a 4-year, and being able to create more pathways for that transfer to the 4-year program requires a kind of translation that I'll get into later. And then finally, this finding your passion, spending some time exploring, right? Expanding your prior knowledge of what was out there in terms of the intellectual landscape at a liberal arts university, and thereby becoming a more well-rounded, in theory, pupil. That's in the category of our serendipitous course suggestion that's intended to give recommendations that students hadn't heard of before, but after familiarizing themselves are interested in. All right, so let's get into it. This is a chronology of things. We have our basic RNN model that used to drive everything, and then our goal-based, and then the cross-institutional translation and serendipitous. Now, of course, I don't have time to give 5 talks, so I'll be talking about these very briefly and encourage you to take a look at the papers. Most of them are open access if you have more questions. And then, of course, ask in the Q&A session. This work all stemmed from an NSF grant, big data grant awarded in 2015. And the big difference between 2015 and 2019 is we started with MOOCs, applying deep learning techniques to MOOCs and recommendation in MOOCs. And then 2016 summer is when we started on prototypes of the recommender system for courses. And you'll see most of these papers have Weijie Jiang in them. She's a PhD student about to graduate from Tsinghua University. She is great. All right. So all of the studies use this basic research data set that we received from the registrar. So about 5 million course enrollments at UC Berkeley over a span of almost 10 years. 160,000 students, almost 10,000 unique lecture courses. That's a big course catalog. And you can see the kind of semester, student ID, course ID, grade, what the major of that student was at the time. It could be multiple majors too, and if it was an undergraduate or graduate student. And then you see how enrollments change by semester. The dip is during the summer. Okay, so for that initial recurrent neural network that drove the system, a recurrent neural network is very much kind of a temporal collaborative filtering model. Instead of the matrix factorization recommendations of people who liked the things you liked also liked this, it's, you could say, people who liked or did the things you did in the order that you did them did this next. And that's what we started with. And the RNN is famously used in language to learn implicitly the structure of language and then try to predict the next word that will occur in a sentence. And so we use that same idea, but analogizing to course sequences, is given a training set of courses. Let's say the training set is 7 years of data, and then we're predicting ahead the next year or the next semester. We're asking the RNN model to complete a student's enrollment sequence. And so when we do that task, we're really asking, is there signal, right? Is there predictive signal in student course selection behavior. Now, if students were always taking the same courses, if their curriculum was calcified and they didn't have freedom of choice, there would be a lot of signal, right? You just predict what anyone of the same major did before and you'll get perfect accuracy. But in American universities, students have a lot of elective choice, and this is the case at Berkeley. So we see here the bottom, the x-axis is the number of semesters of data we had for that student, which corresponds to what year they are at the university, if they're junior, senior, freshman. And this is all predicting the same semester, which I believe is fall 2017. And we have recall at 10, which means what percentage of the courses the student took in fall 2017 show up in the top 10 predictions for that student that the model gives. And so we see the LSTM, I'm using RNN and LSTM interchangeably. It is an all LSTM architecture that was used. Around semester 3, it peaks, which would be the first semester of their sophomore year. And at that point, we're almost capturing half of their course enrollments. And students take between 4 and 5 courses a semester. So within the top 10, we're capturing about 2 to 2.5 of those courses. And you see popularity by major as a baseline, less well, 3 gram less well. Popularity, definitely not a good model. So if we've gotten questions before of, are you just predicting popular courses with such a model? And the answer is no, because the popular course model doesn't do very well. And you can break this out by the different schools and how well the performance is about the same. So we did a little bit of exploration with the RNN model. If we take the hidden state, the student's hidden state of the RNN right before they graduate. So the RNN keeps a hidden state at every semester based on the courses the student took. Therefore, the hidden state at any given semester is a function of everything they've done in the past. We took that hidden state for every student. So every data point here is a student colored by their major. And since it's before they graduate, it's essentially saying this is a summary of the courses they took. So what students have similar coursework is one interpretation of this. And you see cognitive science students and psychology students very close together. The psychology students sort of closer to the social sciences, whereas the cognitive science students closer to STEM. You see computer science adjacent to mathematics, adjacent to statistics majors. So if you're a student and you wanted to declare statistics but didn't get in, you can see what other majors have similar coursework, or if you just want to learn statistics but you don't want to be a statistics major for whatever reason, or computer science major, maybe you can interpret this kind of information. So that's what we started with, just recommending people, other people like you did this next, but that was of limited utility, although students thought it was interesting. What we really wanted is something that allows the student to personalize the recommendation. What a people like you model assumes is that your goals are like people like you in the past. And that might not be true. Every year is different. The career landscape changes, the number of courses changes, politics change, everything changes every year, right? So we don't want to assume you have the same goal as someone like you in the past. So instead of trying to infer everything, we want to ask you what your goal is and see if we can help you get there. So this was an evolution of the RNN model. And here what is happening is, instead of predicting what course a student will take next, it's predicting what grade a student will get on any arbitrary course taken in the current semester. So now we've moved from a behavior prediction model to a performance prediction model. So this is kind of like an assessment model. If any of you have heard of deep knowledge tracing, it's a similar idea where an RNN type structure is predicting performance given past observations. This is a lot more complex than DKT is. We're taking as input the courses and grades you got in the previous semester. So that would be G1, previous semester grades. And then C2 is what courses you're currently planning to enroll in. And we take this into account because the consistency of what you choose to take, I guess you could say your semester load, will affect the grades that you can get on those courses, right? If you only take 2 courses in a semester, it's going to be a way different outlook on your performance in those courses than if we know you're taking 7. Okay. So what is this goal? It can't do anything, but the goal that we're talking about here that we're supporting in this work is the goal of wanting to take a particularly challenging course and to be prepared to take it. So we use this Vygotsky notion of zone of proximal development, but we switch it up a little bit and apply it to a more macro view in terms of courses here. So you have your zone of the courses where if you took the final right now, you would pass the final. So those are things you can do. And there's things you can do, meaning the courses that if you had help, being lectures and peers, essentially what you're supposed to get when you take a course, you could pass the final when you get to it. And then there's the things that are outside of your zone of proximal development, where if you took it, given reasonable amount of time and energy put into it, it would be too much. You don't have the prior knowledge for it. You're not there yet. So what we want to be able to do is model this, model what are the courses that you could pass the final right now, what are the courses you could pass with help, and allow the student to specify a target course that is perhaps outside of their zone of proximal development. Perhaps that is why they're asking for suggestions on if they're ready, because they feel they're perhaps not. And then suggest a course that if they take it, they will then be most likely to bring this target course into that zone of proximal development. And this requires being able to predict a grade, because that is what we use as a proxy for zone of proximal development. Will you pass this class if you take it right now? And in doing that prediction of will you pass this class and what courses might you need to pass a class that you're not predicted to pass right now, the model would need to encode prerequisites. Now, the university already has prerequisites, but they're not comprehensive. They're not updated every year based on new courses. And furthermore, they're not personalized, right? They're static attributes of a course. And it could be that you are a math major and you want to take an advanced machine learning course. You happen not to take linear algebra, but you certainly have all the knowledge you need for linear algebra. So a personalized prerequisite recommendation system could acknowledge that you already have LinAlg and just give you what you need, which perhaps is programming for non-engineers. Maybe that's what you needed. And what we found was that predicting course grades, at least at Berkeley, and I've seen this in other course grade prediction papers at EDM, is hard. We got 75% accuracy versus a 50% baseline, but we had to make the grade prediction problem a binary problem in order to get there. So the binary problem was, did you get the most common grade or not? The most common grade being an A. We were able to, in one of the validations, relearn 45% of the prerequisites that were on the books using a generic a student with no history, and then we inferenced the model to say what would be the best course to increase performance on the target course. And 45% of the time, then it was, or at least 45% of the time, the real prerequisite was within, I think, recall at 10, it might have been. Okay. And then we also did some simulation, kind of going back and seeing in student sequences and saying, all right, which students took a historically difficult course? Now let's rewind 2 semesters. Let's see what course the goal-based recommendation system would have suggested to the student, and then look at the students who ended up taking one of those would-be suggestions, and then how did they perform on that difficult course versus the students who didn't. Now, it's observational experiment. It is not kind of econometric standard evaluation, because there certainly could be a selection bias in the students who chose not to take what would have been a recommendation there. But in any case, the result was that the students who did take what would have been a recommendation at the time did 22% better in terms of GPA on those difficult courses. And we discussed this goal-based approach in a 2019 learning analytics paper, and then we extended a bit in this Rexis paper also in 2019, where we try to do the inferencing more efficiently. So instead of brute forcing it, the way we did in the LAC paper, where we said, okay, for any given course, which course is the one that's going to maximize the probability of performance on the target course, we try a different approach in Rexis. But this model is not yet in production. It's not in our recommender system, and there's a couple reasons for that. One is, I think the killer application for this kind of goal-based recommendation is career-based goals. But we don't have career data yet joined in. We don't have those data at all. There's a organization on campus that we need to reach out to, and there's some negotiation there, and then would we be able to get identifiable data and then link it without asking for permission from the students? That's an IRB question. So there's some effort that needs to go into that. It'd be great if we had course evaluation data to know how students rated courses. And at 22% improvement, I'm not yet convinced that this is trustable enough for students to take this recommendation. I would like first for some other external validation of the recommendation, such as showing faculty student history and then showing them the recommendation of the system for that faculty member's course and asking them to rate the appropriateness of that, perhaps versus recommendation that a non-faculty academic advisor gave and how they compare. And then we also want to make sure that there's not intrinsic equity issues that are impacting the predictions, whereby the model is stereotyping a student, and that kind of ethical or bias in AI research, I think, is important.
Hi, Zach. This is Adil. Can I ask a question?
Yeah.
Is it that the problem is defined as making a single recommendation of a course to get to the target course? Or are you also considering multiple recommendations like a path towards the target course?
Yeah, that's a really good question. We are in the work that I showed here, these two papers, it is single semester recommendation, which could say these are several courses you could take this semester to prepare, but it is not sequential recommendation. Sequential recommendation is on our list. It is much harder, at least with an LSTM architecture, to do that multiple sequence recommendation, because then you have the combinatorics of you could take 2,000 possible courses this semester, right? And now cross that with 2,000 possible courses next semester, which is why we tried to make it a little bit more tractable in the Rexis paper, but that approach still does not accommodate multi-time slice suggestion.
That's great. Actually, you sort of foreshadowed my following question, which was, you spot on, right? You run into combinatorial issues with RNNs. Have you considered modeling the problem with attention networks, like transformer networks?
Yes, that is the next generation.
Excellent.
Yeah. Hard to ignore BERT models, right? You open up your web browser and there's 5 BERT papers that are.
Yeah, we should come up with a BERT for education, right?
Yeah, certainly. I'm sure someone's working on it. Yep. So I think that is the way. The attention models, the contextual embeddings, much more elegant solution to the multi-time slice imputation problem. All right. So Any other questions before we switch gears? So this cross-institutional course translation issue is really important one in higher education, particularly in California. And here there's a little bit of a shift happening from us recommending or creating models that are student-facing versus here it's still a recommender system, but it's more administration-facing. It's telling schools and the articulation officers what they might want to articulate across institutions. And to give you a little bit of backdrop on why this is important in California, 1960, there's this master plan for higher education instituted by the legislature, and it's created 3 tiers of higher education. And this was the UC system, the community colleges, and the California State University system. So among high school graduates, the top 1/8 would be admitted to one of the now 9 University of California campuses, UC Berkeley, UCLA, among them UC Irvine, etc. The top 1/3 would be admitted to one of the now 23 California state universities. San Francisco State University, San Jose State University are examples. And all graduating high schoolers or otherwise capable, let's say GED equivalent, high school diploma equivalent, could enter one of the now 115 community colleges. It was 114, and now we've added an online community college that's currently offering certificates. So graduates, even if you didn't make it into the 4-year university tiers, which are the top 2 tiers, and you went to the community college, which is a 2-year system for the most part, you would still have the opportunity, if you showed your promise at the 2-year, to then transfer into the Cal State or UC system. And of course, getting a bachelor's degree versus an associate's opens up a lot more career opportunities. I know it keeps going up. Oh, now you need a master's, et cetera, but a bachelor's gets you farther than an associate's degree, and is a way of improving kind of your lot in life there. And the New York Times called this California's upward mobility machine. So it is important to the identity of California and our and the UC system as a whole. But the problem here, or I would say that the challenge, is this kind of curricular alignment problem when it comes to transferring from that 2-year to 4-year, which is you have 115 community colleges which have some level of standardization, but like much of higher ed is largely unstandardized. And so the question is 2 years of computer science curriculum at Community College X equivalent to 2 years at the University of California? And more pragmatically, will the student struggle with the post-requisites at a UC, right? And so how can we align these better? How can we perhaps create more, identify more courses that are equivalent, and then make this transition from 2 to 4-year program easier? So course-to-course articulation is that process, is the process of saying which course, if any, at institution A is academically equivalent to a course at institution B. And taking courses at institution A, which might be a community college like Laney Community College of Oakland, that satisfy degree credit at institution B is usually required to transfer. You need to, after 2 years, you need to be, on your way towards earning credit for a particular degree. And as you can see from this handbook, the process for articulating a course has a lot of paperwork involved. The community college has to ask for it to happen. The articulation officer, which there's one at every campus, hands that request to the articulation officer at the UC, or in this case to the UC, and then that person identifies the faculty associated with that course, gives them the request, and then the faculty can approve, deny, or ask for questions like can I see the syllabus? Can I see the average grade in the course? They may ask for a look at the midterm or final. And then maybe a year later, on average, the course is articulated. So that's a lot of work, and it's a slow manual process. And so if we were articulating the entire system from scratch, what would that entail? How much work would that be? And to start to evaluate this, let's only consider articulations between one community college and one University of California school. So on average, there's 1,000 community courses at a community college and about 7,000 at UCs. So all pairwise combinations, the 63 million pairs, but we know that's an upper bound because that's ignoring the department of the course and saying you're going to consider French Lit courses to be articulated to computer science. You're not going to do that. So if you only look at department to department mappings, so all computer science courses within the UC versus within the computer science department at the CC, you still end up with 35,000 pairs to consider across all the departments. And that ends up being 36 million pairs if you're trying to articulate between all UCs and CCs. So a methodological approach, I contend, is needed that can scale to this magnitude. And in this work, we proposed a data assistive, so it's not ready to throw out the human. It still requires human supervision, using course catalog descriptions and historic enrollment patterns to essentially triage this articulation process, narrow down the candidates for the human raters to something tractable. And if that is successful, it'll mean more valid articulations on the books, giving more students greater credit mobility, more ways to qualify for transfer. Fewer wasted credits will mean there's 42% of credits are thrown away when students transfer on average. Fewer wasted credits means less financial aid burden because you're not essentially wasting those semesters in terms of counting towards a degree. It may be intellectually enriching, but you're not going to get those won't be brought to bear for a degree. And then further, if it's successful, the approach could generalize to other credit acknowledgement scenarios, like going from K-12, taking honors courses to college, or going from the military to college. There's a lot of credentialing, there's a lot of work experience that give people skills that is difficult to articulate to a degree, but that might be something we increasingly want to do. So the data set for this work is a novel data set that has UC Berkeley enrollments and catalog descriptions of courses and community college, this one community college. You can see Berkeley's course descriptions are a little longer, 325 words per description versus the community college that has 27 words, but both schools have outliers that have less than 10 words in them. And we have 65 existing articulation pairs to validate against. And we have 184 degree satisfying courses that have no articulation to the CC. And there is definitely going to be a good portion of those that will never have. As you can see, there's 1,000 courses at the community college and almost 8,000 at the UC. There's just not as much coverage. But are we missing something? And that's what we're aiming to answer. So here you see the UC course that is articulated to the CC course. Some require 2 courses at the community college to articulate to 1. And then here, the last one is not articulated at CC1. So as a reminder, here's the task. We have a catalog description, and is this course equivalent to any course at Laney, such as this one? It has a similar title, data structures, and then data structures and algorithms, shorter description. Is it a match? And so our methodology is to validate the models of cross-institution course similarity using those 65 articulated pairs, and then generate candidate articulations for a subset of the unarticulated 184. It's still a human supervised process, so we don't want to overwhelm the human that's going to be evaluating this. So we do a subset of the 184. And the way that we're going to evaluate, or the way we're going to infer similarity is with a variety of models. Some are content-based, meaning they're using the catalog description. So we have our basic bag of words model of a course, TF-IDF model that downweights words common across course descriptions. And then we have what we call DeskVec, which is just running all of the words in the course description through Word2Vec and then averaging all of the word vectors. You could say that might have the benefit of two courses that are actually similar conceptually but use synonymous words that are different, would be considered similar by DeskVec, but perhaps not by bag of words. And I'm going to breeze through Word2Vec to be mindful of time. But it's a hugely popular model that's used to make meaning of words in a linear space. So it creates a linear vector space that you can do manipulations like king minus man plus woman equals some vector, and that vector's nearest neighbor is the word queen in that space. So it's a very interesting kind of emergent semantics, emergent concepts that it seems as though this skipgram, which is a specific kind of Word2Vec model, continuous bag of words is another, is learning. Okay, and I'll just show these in case someone wants to rewind and then look at these slides. Okay, but it's this representational layer, which is the middle hidden layer, that is so valuable and can be used to complete analogies like Francis to Paris as Italy is to, and then the algorithm, that vector space returns Rome. And then you see the relationship between countries and their capital if you reduce the dimensionality down to 2. So it is learning some concepts. So back to courses here, we have all of this non-content data, right? All of these enrollments that aren't being used by the content models. We have sequences of student enrollments. So instead of analyze the content of a course, we're going to analyze the context to represent the course by running the skipgram model over course enrollment sequences, as you see such a sequence here. And we call this course2vec. So the idea here is, can a skipgram model applied to course tokens in many course enrollment sequences embed courses into a concept space the way words are embedded to a concept space? And if it can, then it is essentially featureizing the course, which could allow you to have a robust representation of similarity. So here's the course2vec. So now we have a course2vec representation, which is a 229 size vector for UC1 and 20 size vector for Laney. The smaller vectors tend to correspond to smaller vocabulary size. In this case, Laney had almost an order of magnitude fewer courses. So we have the course2vec model, and then we also will concatenate, just naively concatenate, the vector that was based on context, which is course2vec, with the vector of the course that was based on content, which is DeskVec, to see how well that does. I see a question of, would adding syllabi to course descriptions improve accuracy? That's a very good question. We're looking into it. Syllabi data is hard to get, though, in clean form. All right. So a little bit of exploration here. If we now take that course2vec vector at UC1, reduce it down to 2 dimensions with t-stochastic neighborhood embedding, which is a common dimensionality reduction technique used on neural networks. It's a non-linear technique, so there's a kind of manifold projection. We get this visualization of courses and colored by, I believe, the department. And let's do the same thing for Laney. What you see is some interesting symmetry in the positionality of the departments relative to one another. And this is what allows you to exploit machine translation. Right now, if we said what 200 length vector in Laney is similar to the 229 length vectors in Berkeley, we couldn't do it. Even if they were the same length vectors, they're trained independently. So it's not the same coordinate basis that is learned. But because of these symmetries in the structure, you can learn a linear translation between the spaces. And this is what it underlies modern language translation. You can train a word-to-vec model on Chinese independently of English, and then based on just a handful of word-to-word translation pairs, learn a linear translation between the spaces. And that's what we do here.
Hey, Judge.
Yeah.
Any implementation of universal sentence encoder in the previous part you implemented TSNE, but will it improve with the uses of universal sentence encoder?
Will it improve what?
If we use the universal sentence encoder.
Universal sentence encoder. I haven't heard of that.
Yeah, it's the another Google proposed recently and is widely used.
Okay. There's sequence-to-sequence models. There's BERT models. Contextual embedding models. Is universal sentence encoder a kind of BERT model?
Yeah, it's a combination of, but it has widely used in terms of if there are multiple texts and multiple languages.
Yeah, so that's probably a contextual embedding model, which means it doesn't specifically do vocab to vocab. It does sentence to sentence. Right, so in the sphere of contextual embedding models and then non-contextual embedding models, you still see a lot of non-contextual embedding models used when you want to go token-to-token translation, like pair-to-vec, and there's other kind of variants of the skipgram that are still viable in terms of benchmarks. I think there probably is a good way to exploit the sentence-to-sentence translation, but I don't know that it would be a better fit for course-to-course translation.
Yeah, thank you.
I'll look into it. Yeah, thanks for the suggestion. So we have the 65 articulation pairs, and for each of the representational methods, we're going to suggest n candidate courses from CC1 to articulate to each of the 65 UC1 courses. And then we're going to do recall at n. We're going to use a leave one out cross-validation to train that linear translation of the course to vec. And here's the results. The n is at the bottom, so this is the number of suggested courses. And then the recall performance is the y-axis. Recall will go to 100 as the number of courses gets closer to the total number of courses at CC1. Okay, so bag of words, if you're only giving 5 suggestions, scores about 0.63 or so. TF-IDF, a little bit better. Running the words through word2vec does better with greater number of n, but it does worse with fewer n. And then for the first context-based method, course2vec, it does pretty much worse across all n. You can see at 50 it catches up, but for the most part it's not doing that well. It's certainly not at 5, it's at 0.5, while the others are more than 0.1 better. But if you now concatenate the course2vec vector, naively concatenate, with desc-vec, you do better across all n. So there is some novel information about a course that's being captured by course2vec. And then we did some exploration where you see some more of the symmetry happening. And we generate these reports for the community college. So course2vec's not available without enrollment data. That's a big downside, and it's hard to get enrollment data. The translation method requires existing articulations, and accuracy is not that high enough to use without human validation. We also need to be checking the efficacy of our articulations with regard to outcomes. So if we articulate a course such that the student can take it at the community college instead of at the UC, how do they do on the post-requisite, right, at the UC? Are they just as successful if they only took it at the UC? Enrollment data does provide that complementary information about courses. Perhaps it encodes difficulty, whereas the description may not necessarily encode difficulty. Descriptions at least aren't naively going to say this course is easy. I think the data system method here can narrow down the articulation candidates at its current accuracy, making greater articulation tractable. So future direction, one is to explore translation methods that don't require existing pairs. There are unsupervised techniques like Muse by Facebook and so forth that learn translations without those existing word-to-word translations. They're not as accurate in unsupervised mode, but it's something to explore. And then this work is being implemented in the City of University of New York system with 2 schools that are now forming faculty committees to look at our articulation recommendations as a pilot, and that might be expanded to the rest of the 19. So I see we're short on time here, so I won't get into serendipitous recommendation. I will just page through it here in case people want to take a look later. And I'll end with the conclusions here. Content and context can be combined to form a more powerful representation, right? So if you have both, try to leverage both. This representation can be repurposed for many tasks: the translation task, course similarity task, and another task, which is inferring keywords from courses that aren't necessarily in the course, well, of course, that aren't in the course description, but essentially, what are those features that are being learned in the course dev model, right? What are the semantics behind those features? And we've looked into that. RNN models or temporal models can be used to infer prerequisites and predict performance, but it's difficult to predict grade. And finding the appropriate model for the task required offline testing, communication with our university administration, and a lot of user testing to understand what was the right model as perceived by the user. Because we had instances, such as in that serendipitous study, where the best offline evaluated machine learned model was not the best model as rated by the users. So those are my takeaways, and thank you to Pravin, Michael, and Alina for the invite, and to everyone at ACTNext. Thanks a lot.
All right, thank you, Zach, very much. Will there be questions from the audience? Everybody is mildly amazed. All right, take a few minutes.
This is John Whitmer. Hi, Zach.
Hey.
Hey, a question. I wanted to follow up on the last point that you made about users, the students especially, not accepting the best rated algorithm by the metrics of the accuracy. Can you say a little bit more about that, about both the student evaluation, and maybe if we got serendipity we didn't get to review, but anything else maybe related to the other recommendations from the other experiments that you performed, the feedback that you got, and any insights you're taking forward?
Yeah, be happy to. So one of the offline validations that we ran was how well does the representation identify pairs of courses that are so similar to each other at the university that there's credit restrictions on them. You can't get credit for both. You can only get credit for one. So that was a source of truth. And our machine learn model, our course of model, performed best on that. It also performed best on a validation set that we created of analogies, like this online course is to this non-online course, is this online course is to this non. And the course of ec model did much better at completing those analogies than, let's say, Bag of Words. But when we generated recommendations for students based on a favorite course of theirs, we said, tell us your favorite course. Now we use one of those representation models to show them similar courses across different departments. That's how we get the unexpectedness is diversifying by department. They rated the Bag of Words model as the highest balance between successfulness, meaning they want to take it, and it's unexpected. It was close, but Bag of Words was higher. And the takeaway, or my hypothesis, or what I took away as a lesson from that, is kind of explainable AI, explainable recommendation, where we were only showing them the course catalog description, which is what Bag of Words is based on.
Yeah.
So if the course of ec was picking up on some latent topic of similarity that allows it to do well at the credit restriction task, that those semantics aren't being surfaced in the recommendation to students. So students may see that recommendation, say, reading this description, I don't know why you're telling me this is relevant.
Okay. And you did not surface that intent, and you surfaced that for both, and it was just you think that their observation of that, the similarity versus lack of, is what drove them to be more find the Bag of Words a better approach?
We showed course descriptions in both. We didn't show any latent semantics in either, and it's my hypothesis, which is testable, that is perhaps why they rated Bag of Words more highly. Or I should say that is why there's this dissonance, right, between the ratings of the models in the online and the offline.
Yeah. That's interesting. Thank you.
Yeah.
Right, we have time for a couple more questions. Anybody wants to phrase it? Well, but let me ask you one. So you are focusing on sort of student navigation within the university grounds and out of the university into the career. If we start to think about students that go into the university, going to college, that either took advanced placement courses that University of California system has control over, and all the course descriptions are similar to what you used to, or even if the course descriptions from just about any high school in California, United States, the world, is available, how would you see your methodology change, if at all? What other factors would you consider? Would you be up for this task to try to navigate kids from high schools into the university, outside the university, into the career?
And we have access to all of the catalog descriptions of the courses. Is that what you're saying?
Yes. Let's say stick to English. Just.
Yeah. I mean, I would proceed cautiously with just catalog description alone between the at the college level. You see the accuracies around 0.6, recall at 5. And then when you add the behavioral stuff, it goes up to 0.7 or so. So in high school, there's a lot less elective choice. And so you wouldn't have that context signal to rely on. And in your situation, you're just saying, we only have course catalog information. Yeah, I suppose it could also be used to triage.
Then you can recommend colleges once you have the high school record, the last 2 years, the last X years.
Oh, the record. We have their grades as well?
Well, let's say grades and they took maybe advanced placement courses that universities administer.
Yeah, well, I mean, in that case, it's very similar, right, as the scenario we have right now between the 2-year and the 4-year schools, but now it's just shifted down to between K-12 and higher ed. But I would say there will be a little bit of loss, likely, in the representational information coming from the context, coming from the course selections. So it'll just be overall lower accuracy at doing that articulation. And I have to say, I've spent most of my time focused on higher ed, so I don't know the nitty-gritty of like where the need is at K-12. I do know as much that in terms of teacher pipeline, that is training teachers who will eventually get the credential in California to become teacher ready in public schools, that starts in high school. They really try to get them on that track in high school. So I know there's a lot of those kind of in the weeds issues with kind of getting a student on track or making that track available and making them aware of that track. But yeah, I would want to investigate more the high school context before satisfactorily answering your question.
This effectively concludes our 28th Tech Talk. Thank you, Zach, for your presentation. If you could transition to the next slide. This was actually our first Tech Talk when the presenter was remote. I hope you enjoyed it. I hope Zach enjoyed it as well. The next Tech Talk, number 29, would be Benjamin Dianovich, and he will talk about the master model. Zach, if you're interested, please tune in as well. I think we could loop you in if you are if you want to know more.
Thank you. Thank you.
With this is the top of the hour. Thank you very much for coming. Thank you, Zach, and we'll see you next time. Thanks.
Thank you, guys. Thank you, everyone.
Thanks. Bye-bye.